we will want to give them 5 minutes more. Brother, please do let me know if we can start. Brother Coco, are you around? Okay. Hello, everyone. It's 6 minutes past 9. I think we should start. We were waiting just a little bit, 5 minutes, so that we ensure everyone joins. I hear that there's someone that says I cannot hear anything. No, we were just waiting for a few minutes. to allow everyone to log in. I will try and open a video, but I'm opening it from the laptop, so it might die in the middle of the lesson. When that happens, don't be shocked. I will be left with the tablet that I'm using to facilitate the lesson, nonetheless. Am I audible though? Is there anyone that can hear me? You can just raise a hand or unmute and say that you can hear me.
Yeah, I can hear you.
Oh, very well, very well. That's nice. That's nice. Okay. My name is Awonke Nqayiya. Today we will be doing a revision on paper 2, of which you will be writing on a Monday, which consists of 4 chapters: statistics, analytical geometry, trigonometry, and Euclidean geometry. It's a very short time that we have together, so we might not be able to do everything that can make you fully ready for Monday. But I will try by all means to touch here and there to give you a taste of what you may expect Monday. And just to give you a few tips here and there, things that you can learn and put as part of the tools or part of the knowledge that you will be taking it with you to the exam hall on a Monday. So let's get into it. I will start with Euclidean geometry, and then we will go to trigonometry, and then we will finish off with analytical geometry. I don't think we will have time to go to statistics. So we will do these three chapters. Even in those chapters, we won't do everything. I will just touch here and there just to give you an idea and tips along the way that you can take with you. I think there's someone that is unmute. Can you please? Yeah, thank you very much. Thank you very much. Well, as I've said, we will begin with Euclidean geometry, which is the work that comes directly from other previous grades, but most importantly, grade 11 and grade 12. It's a combination of that. There are questions that I want to highlight during this lesson. There are questions that I want to highlight. They come up more often. If you look at 10.1.1, there you are required to prove that some quadrilateral is a cyclic quadrilateral. That comes up more often. If you look at question 10.1.3, you are required to prove that 2 triangles are similar. That as well comes up more often. Another question 10.2, which is the use of what you have just proven, the similar triangles, that comes up more often as well. So I think if I use that method of touching on the questions that come up more often on the previous question papers, then we should be fine. So let us take a look in this example. It's a full question. It consists of 17 marks. Euclidean geometry is one of the chapters that contain a lot in paper 2. So it's important that you familiarize yourself with the solving methods on that chapter, which is Euclidean geometry. So in that question we are given, I think this comes from 2016. I think it's a question paper that was written in 2016. So in the diagram, a circle, there's a circle passes through D, B, and E. So that is the circle. It passes through those 3 points, D, B, E. And then we are given diameter ED. That ED over there is the diameter of that circle. So they say diameter ED of the circle is produced to C, and AC is a tangent to the circle at B. You see, when it comes to, especially to Euclidean geometry, one of the most important things is the proper analysis of the given statement. Because a lot of what you are going to do when you answer those questions rely on what was said in the statement. So if you get the understanding of the statement and you analyze it properly, most of the time you will end up answering a lot of questions before they are even asked. For example, we are told that ED is a diameter in that diagram. ED is the diameter in that diagram. So once you see the word diameter, there must be a lot that comes across your mind with regards to what is a diameter and what are the properties of a diameter. One of the properties of a diameter when it comes to Euclidean geometry is that it subtends 90 degrees at the circumference of that circle. So if you look at that diameter, ED, and then you move from point E to the circumference, you reach B, and then you move from point D, then you approach the circumference, you reach point B again. You will see that, okay, that diameter subtends an angle at the circumference of that circle. Okay, my laptop will shut down just now, but it's fine. We will proceed smoothly, but the problem is that you won't be able to see my face, but you will still hear me. So if you look at that diagram, B2 is the angle that is subtended by that diameter. So by analyzing and reaching that agreement, you can conclude and say that, okay, angle B2 is supposed to be 90 degrees because it is subtended by that diameter. That might be useful when you answer those questions that are following. That might be really useful. So it's very important that you analyze the statement properly and analyze it word by word. That is what I would recommend. Another thing that you see there is that we are told that AC is the tangent to that circle at B. So there is AC, which is the tangent to that circle at B. When they tell you that there is a tangent, then a lot of that revolves around a tangent should become active at the back of your mind. For example, there is one theorem from grade 11, I think the last theorem, theorem 7 to be specific. That theorem has some sort of a statement that revolves around the tangent and the chord. So if you see that there's a tangent AC, and then there is a chord DB. And those two lines, the tangent and the chord, they meet at an angle. They meet at a point B, and then they form an angle B1. So that theorem says that that angle between the tangent and the chord, which is B1 in this case, that angle is equal to the angle subtended by that chord in the alternate segment. So the angle between the tangent and the chord, which is B1 in this case, is equal to the angle subtended by that chord in the alternate segment. So if we make a conclusion then from this statement is that B1 is supposed to be equal to E. That is something that we draw from analyzing that word, that AC is a tangent to the circle B. Another conclusion that we would make here is that there is another angle formed between this tangent AC and chord BE. Between the tangent AC and the chord BE, there is that angle that is formed there, which is angle B3. So that angle B3 should be equal to an angle subtended by that chord in the alternate segment. So what is that angle that is subtended by BE in the alternate segment? Who wants to take a guess? Is it, sorry?
Isn't it C?
The chord BE has to subtend this alternate angle at the circumference of the circle, not outside. If you look at C is outside the circle.
So it's D.
Sorry?
So is it D? D2.
You have to be specific because there are a lot of angles at D. You can say D1 and you can say D2 to be specific. So when you say D, it becomes confusing. So which one?
D2.
Yep, that is D2. So by analyzing that statement, we can, thank you very much for that. By analyzing that statement, we can conclude that B3 is actually equal to D2. And the reason for these conclusions that we have made, we write it as tan-chord theorem. It's an acceptable notation. You write tan-chord theorem. I think just one most important thing to mention is that if it happens that there is something that you do not understand, please feel free to let me know. Please feel free to stop me in the middle of whatever that I'm saying at that moment in time. It's important that we move together forward so that we don't leave any learner behind. So please do let me know. You can just unmute and talk, because when you raise a hand, I will not be able to see. So we have made two conclusions, that B1 is equal to E, B3 is equal to D2. And there is a common reason for that. We say tan-chord theorem. Tan-chord theorem. That's an acceptable notation. So let's move forward with the analysis of the given statement. We see that there we are told M is a point on DE such that AM is perpendicular to DE. So there is AM, that vertical line. We are told that vertical line is perpendicular to the diameter, which is DE. So once you see perpendicular lines, then you can expect 90 degrees somewhere there. That means M1 is 90 degrees and M2 is 90 degrees. Perpendicular lines form an angle of 90 degrees where they meet. So M1 is 90 degrees and M2 is 90 degrees. And then we say that chord BE, there is chord BE, which intersects at F to form angle F1, F2, F3, F4. So that is the statement that we are given, and that is how we have analyzed that statement. So now we are going to dive deep into the questions. The first question that we deal with is 10.1.1. Is there any question with regards to the statement that we have just analyzed? before we get into the questions, before we get to answering the questions from the question paper. Are there any questions from you? Okay. Silence hopefully means all is well. So we are required to prove that FBDM is a cyclic quadrilateral. FBDM, it's important that you get to see this, the figure that we are talking about exactly from that diagram. FBDM. There is no cycle around these 4 points, but there is an imaginary one. So they say that prove that FBDM is a cyclic quadrilateral. So when they tell you to prove that FBDM is a cyclic quadrilateral, it's very important that you ask yourself, if this was a cyclic quadrilateral, then what would happen? If FBDM was a cyclic quadrilateral, then what would happen? And then once you get to understand what would happen, you then prove exactly that thing that would happen. For example, if FBDM was a cyclic quadrilateral, then you would see that, okay, M2 would be an exterior angle of this FBDM. That M2 over there would be an exterior angle of this cyclic quadrilateral. And the exterior angle of cyclic quadrilateral is expected to be equal to the opposite interior angle of a cyclic quadrilateral. That is what is expected. The exterior angle of a cyclic quadrilateral is expected to be equal to the opposite interior angle of a cyclic quadrilateral. So if we want to prove that FBDM is a cyclic quadrilateral, if we want to prove that, then we must show that M2 is indeed equal to B2. That is what we have to show. So when you do that, you do not just jump and say M2 is equal to B2. There is some steps that you have to take prior to that. So what we are going to do is that M2 is equal to, you will write and say M2 is equal to 90 degrees. I think that is the information that was given from the statement. So you can write it, this is given, or you can write AM is perpendicular to DE. That is what you can write. M2 is equal to 90 degrees. The reason for that, it's given, or you can say AM is perpendicular to DE. And then the next step that you have to take is to calculate the value of B2. And you check that if this value is equal to B2, then that means those two angles are equal. Calculate the value of B2 aside and check if that value is equal to 90 degrees. If that value is equal to 90 degrees, then that means it is equal to it is equal to M2, which is the exterior angle of a cyclic quadrilateral. Then you have proven that, oh, actually this is a cyclic quadrilateral. So the next step is to say B2 is equal to 90 degrees. Why is B2 90 degrees? Who wants to give us a reason? Any take?
Exterior angle.
Sorry?
Exterior angle.
No, B2 is not an exterior angle. The reason why
it's angles in a semicircle.
Yep, angle in a semicircle or angle subtended by the diameter. Angle in a semicircle, you can write it that way. Angle in a semicircle. circle or angle subtended by the diameter. So that is what we have done so far. We calculated the value of M2 and put it aside. We got it to be 90 degrees. And then we calculated the value of B2 and then we put it aside. We got it to be 90 degrees as well. So we check now if these two angles are equal. If they are equal, then it validates that assumption that we made, that if F, B, D, M is a cyclic quadrilateral, then M2 has to be equal to B2. So if they are equal, then this is a cyclic quadrilateral. So what we are going to do now is that, therefore, M2 is equal to B2. You can write a reason for that, or maybe you cannot, it's up to you. If you want to write the reason, you can say is both, you can write both equal to 90 degrees. And then you conclude, therefore, F, B, D, M is a cyclic quadrilateral. You write that long word there. The reason for that, you have proven now that the exterior angle, M2, is equal to the opposite interior angle. That is what we have just proven, which is M2 is equal to B2. That is what we have proven. So that will be the reason for your conclusion that, okay, this is a cyclic quadrilateral. So that will be your reason that, oh, okay, the exterior angle of a cyclic quadrilateral, the exterior angle of a cyclic quadrilateral, that is quad, but you will have to write it as quadrilateral. I'm just running out of space. The exterior angle of a cyclic quadrilateral is equal to the opposite interior angle. So that is how we proved that this is a cyclic quadrilateral. If you remember, this proof was based on a question that we asked ourselves. As they said, prove that FBDM is a cyclic quadrilateral. We asked ourselves, if FBDM was a cyclic quadrilateral, what would happen? What would be a fact? And then we move along, we prove that fact, and then we conclude that if that fact holds, then this is indeed a cyclic quadrilateral. Are there any questions with the approach that we have used, or should I move to the next one?
Yeah.
No questions. Okay.
I have a question.
Okay.
Could we also say that B2? Okay, we proved that B2 was 90 degrees, right? Because it was angled in a semicircle. And then obviously M1 is also 90 degrees because it's angled in a straight line. So can't we say that opposite angles are supplementary?
Yep, you would take that approach as well. There are three things that you check when you want to prove a cyclic quadrilateral. So what we have just done is one of them.
What?
And
So is everything that you wrote here 1 mark?
No, it's 3 marks.
Oh.
No, I'm saying that you have 3 options. You don't necessarily have to do all of them. You can just choose one.
Oh, okay. Thank you.
So what we have just done here is choosing one option, which is to prove that the exterior angle is equal to the opposite interior. The exterior angle of a cyclic quadrilateral M2 is equal to the opposite interior angle, which is B2. So that is the option that we took. Another option that you have is to prove that when you add the 2 opposite interior angles of a cyclic quadrilateral, they should give you 180 degrees, which means opposite angles of the interior angle of a cyclic quadrilateral So opposite angles of a cyclic quadrilateral are supplementary. So that is basically that. So you would say that B2 is equal to 90 degrees, like just how we did semicircle. And then you would say that M1 is equal to 90 degrees. You would say AM is perpendicular to DE, or it's given, or angles on a straight line, depending on your choice of a method. And then after calculating those values of M1 and B2, you would say that M1 plus B2, because these are opposite interior angles. And then you know that M1 is 90 plus, you know that B2 is also 90 as well. And then when you add those two values, they give you 180 degrees. And then that allows you to conclude that this FBDM is indeed a cyclic quadrilateral. That allows you to make that conclusion. But then you wouldn't justify the conclusion with the reason exterior angle of a cyclic quadrilateral. You would justify it with what we have done, which is opposite interior angles of cyclic quadrilateral are supplementary. So that is what you would choose as a second option. A third option is a case whereby you have to show that if let's say there were chords there, if there were a lot of chords there, and then you would sort of look for angles subtended by the same chord and you would like to show that these two angles are equal. So that is the third option, but we do not have those lines that cross now in that suspected cyclic quadrilateral. We do not have those lines. If we did, we would it would still be one of the options that we would have explored, but those two lines that cross are not there in this case. I think I should move forward to 10.1.2. Please feel free to stop me if you have a question. And then now we move to question 10.1.2, where we are required to show that B3, where is B3? There is equal to F1. B3 is equal to F1. B3 is equal to F1. So are there any ideas who wants to step out of the closet and give us some insights in solving this problem? We want to show that B3 is equal to F1. Before you get into it, I think it's important that I mention that we just proven that this FBDM is a cyclic quadrilateral. So moving forward now, answering the questions that come after that, we can use this as a cyclic quadrilateral, and we can use the properties of the cyclic quadrilateral. So whether you succeeded to show that this is a cyclic quadrilateral or you did not succeed, you can use it still in the upcoming questions. You had an idea?
Yeah.
Okay.
Can I answer?
Sure.
So we can say that B3 is equal to D2, tan chord theorem, and then D2 is equal to F1 because it's in exterior angles of a cyclic quad.
Okay, thank you very much. That is absolutely correct. That is absolutely correct. He is saying that, okay, we want to prove that B3 is equal to F1. So if you remember, where is the diagram that had my lines? Yeah, I want this one. Yeah, we will use this one most of the time, because this one has the information that we analyzed from the given statement. So he is saying that B3 is equal to D2. And this is something that we have seen when we were analyzing the statement. So hence I've said earlier that one of the most important things in Euclidean geometry is the proper analysis of the given information before you even go to the questions. So B3 is equal to D2. Why do you think B3 is equal to D2? You did not justify. What is the reason? B3 is equal to D2. What is the reason? Because in Euclidean geometry, reasons are expected. Where's the guy that was answering?
Yeah.
Okay, you can just give a reason on his behalf.
Tan-code theorem.
Tan-code theorem. Yeah, it's a Tan-code theorem. Tan-code theorem. Blah, blah, blah. You will write theorem. So we have seen that B3 is equal to D2. So now we will have to establish a relationship between D2 and F1, the F1 that we want to prove. Establish a relationship between D2 and F1. We see that, actually, we said that this is a cyclic quadrilateral, which makes now F1 an exterior angle of the cyclic quadrilateral. And we have seen before that the exterior angle F1 has to be equal to the opposite interior, which makes F2, equal to D2 as well. Exterior angle of a cyclic quadrilateral. You will write cyclic quadrilateral in full. I'm just saving space. So you see now that, actually, no, it's not F2, it's F1. It's not F2, it's F1. Sorry. Now you see that actually F1 is equal to D2, B3 is equal to D2 as well. So you can make a conclusion. Therefore, B3 is equal to F1. You can justify that or you cannot. I don't think it's so important. If you want to justify it, you can say both equal to D2 because they are both equal to D2. Are there any questions with the one that we have just done? So that we move quickly to the similarity question. Okay, no. I'm assuming that silence says I'm happy. So let us now do question 10.1.3, which requires us to prove that triangle CDB is similar to triangle CBE. This is one of the questions that tend to come up a lot from the exams. This is probably one of the reasons why I picked this question in preparation for this lesson. This is really a nice question when they say prove that certain triangle is similar to a certain triangle. When they ask you that question, just know that they are giving you those marks for free, for mahala. Just know that though that question, as much as it's a question, but it also has the answers for you. You just have to give the reasons why this is the case. For example, if you look at what is written here, especially the order in which this is written, we have triangle CDB, and we want to show that it is similar to triangle CBE. Before we go to the diagram, let us talk about this, this arrangement. Here, when we prove that a certain triangle, two triangles are similar, if we prove that two triangles are similar, for example, let me just make a brief example. We have to show that their corresponding angles are equal. This angle, we have to show that it is equal to that angle. And that angle, and on top, we have to show that it is equal to that angle on top. And then that angle on a far right, we have to show that it is equal to that angle on a far right. So that is what we have to do when we show that two triangles are similar. And it's okay if you find out two of them are equal, and then you write the third set of angles as a third angle. You just say that, oh, okay, this angle and that angle are equal. The reason for that is third angle. You would have said just previously that the angle at the top is equal to the angle at the top. The angle on the far left is equal to the angle on the far left. And you will provide the reasons for those statements. And then when you have found the reasons for those two angles, that pair of two angles, you just have to say that the angle on the far right is equal to the angle on the far right on the other side. The reason for that is third angle.
Sir.
Hello?
I'm sorry to interrupt you. May I please get permission to record this? Because where I am right now, people that are playing music, I don't hear you well.
Okay, no, it will be recorded. You can just, you can record on your side, but it will also be recorded as well. I think it will be available on Facebook, on YouTube as well. So yeah, I think it's fine. You can go on and record for yourself. So, as I was saying, it is easy to see when these triangles are arranged in that manner. It's a beautiful manner. You can see that, oh, okay, this angle is corresponding to that angle. That angle is corresponding to that angle. And the angle on the far right is corresponding to the angle on the far right. But it's a hectic moment if you get those angles in that shape, in that diagram over there. It becomes really untidy and uneasy to see which angles are equal and which angles are not. But from this arrangement, we get it easy to see which angles are equal to which angles. We have triangle CBD similar to triangle CBE. So that first C over there in that triangle CBD has to be equal to that C in that triangle CBE. You just have to find a reason why that is the case. That angle D, the second angle, the second letter in that triangle, is equal to that angle B, the second letter in that triangle CBE. You just have to find the reasons why these angles are equal. That angle B in that triangle CDB is equal to that angle E in that triangle CBE. You just have to find a reason why this is the case. Hence, I'm saying, as much as this is a question, but it also has answers. So when they ask you that, prove certain triangles are similar, just know. They're saying, marks for free. Just rejoice. But one thing that you must be careful of is to be able to identify this triangle CDB, so that when you talk about angle B, you are able to say, okay, that is angle B1, or that is angle B2, that is angle B3, not just B, because B will be confusing. There are a lot of angles there at B. It has to be B1, B2, or B3. Hence, it's important to identify that triangle CDB. So let us get into it. Let us find the first set of angles that we think are equal. Firstly, let us go and check for this triangle CDB. There is CDB, that triangle CDB. That is what we are looking at. So when we talk about angle C, we mean that C. When we talk about that angle C, we mean that C. When we talk about angle D, we mean that D1. Who wants to tell us, when we talk about this angle B, which angle do we mean out of those B? When we talk about that B?
B1.
B1.
We mean B1 because B1 exists in triangle C, D,
B.
Yep, excellent. That is an absolutely correct answer. Let us move to this triangle CBE. There is triangle CBE, the bigger triangle, triangle CBE. So if you look at that triangle now, when we talk about B, we talk about B1 plus B2. We talk about B1 plus B2 when we talk about the bigger triangle CBE. When we talk about angle E, we talk about that E. When we talk about angle C, we talk about that angle C. So if there is, only one angle at C, it's okay to write just angle C. But if there are two or more angles at a point like D, it's not correct to write C. It's not allowed to just write D because there are a lot of angles at point D. But as for point A, point E, and point C, it's allowed to just write C, just write A, just write E. So let us get into it. Which angles do you think are equal there? And what are the reasons? What is the reason? Who wants to take an informed guess?
B1 equals E. That's 10 chord theorem as we proved before. And C.
I didn't get you.
B1 equals E.
B1 is equal to E. Absolutely correct. This is something that we have seen from the analysis of the statement. So let me write that down and then you will answer the second one. B1 is equal to E. The reason for that, the guy said it's tan chord theorem. That's absolutely correct. You will write theorem in full. I'm just running out of space. This is something that we have seen from the analysis of the statement. Hence, it's very advisable, well, from my point of view, that you analyze the statement proper, well, from the point of view of Mr. Ngolo as well, because he's the one that taught me this, the importance of proper analysis of a given information, Mr. Ngolo. So let us then move to the second question, to the second angle, to the second set of angles. You were saying it's what?
Also C equals C, that's a common angle.
Yep, C is equal to C, that's a common angle.
Then D1 is equal to B2, this is the third angle of the triangle.
You said E1? Sorry, you said which angle?
D1 is equal to B2, that's just a third angle of the triangle because we already solved the two other angles. So of course it will be
D1 is equal to B2.
No, sorry, wait.
B is equal to D.
To B, sorry, B, my bad. B, sorry.
Yeah.
Which B?
Both 1 and 2.
B1 plus B2.
Yep. Yep, you have to be specific. We say that according to the arrangement, D has to be equal to B. So which D? We talk about D1 in triangle CDB.
Yeah.
Which B in triangle CBE, CBE, that is B1 plus B2. So D1 will be equal to B1 plus B2. D1, okay, my pen is playing games with me. Well, again, D1 will be equal to B1 plus B2. What is the reason for that?
I say third angle triangle.
Yeah, third angle. If you look at the diagram that we are given, it is not so clear as to what is the reason why these two angles are equal. D1 equal to B1 plus B2. It is not so clear from the triangle, from the diagram. Hence, this one, we end up using it as the third angle sort of reason. And then we say, therefore, the triangle CDB is similar to triangle CBE. The reason for that, what do you think is the reason for these two triangles to be similar?
Angle.
Yep, angle. We have proven just above that three angles are equal. Angle. Then you are done. So that is how you tackle the question of proving similar triangles. Honestly, if they ask you that question, just know that now they're saying free marks. So I'm trying by all means to not just answer these questions for you, but in the process, I'm trying by all means to give you the sort of the thinking process behind answering these questions, which is what I think is one of the most important things in mathematics, the thinking process, so that you are able to expand on that thinking process, apply it on as you do the exercises on your own at home, and also apply it on the exam room. So let us now move to 10.2. We are given there that CD is 2 units. We are also given that the diameter itself, DE, is 6 units. CD is 2 units. DE, the diameter itself, is 6 units. What do you think is the unit for CE? How many units is CE?
8.
8. That will be C2. That will be CD plus DE, which is 2. 2 plus 8. A question like this normally follows from what you have proven previously with regards to similar triangles. So we say that CE will be equal to 8. And now they want us to determine the length or calculate the length of CE. Where is CE? There is CE in that triangle. In that side, there is CE. The approach that I would recommend here is that you do not play so far from what we have just proven with regards to the similarities. Because most of the time, this question revolves around exactly that. So we will try and go back to what we have proven, try to use it here. So whether you managed to prove it above or you did not, please do use it in the following questions, because it's useful. So they want us to calculate BC. If you look at the two triangles that we just proven to be similar, we have two sets of sides called CB. There is that first side from the first triangle, and there is the second side from the other triangle. So now we have to decide which triangle are we going to use. We will decide based on what is given already. We know that CD is 2 units. So if you look at that triangle CDB in that expression there, that means that side CD is the side that we have to use, because we are given that side as 2. Another side that corresponds to CD, we want to take as the side that corresponds to CD on the triangle that is on the right. CD corresponds to which side?
CB.
CB, yes. CD corresponds to CB. So if you look at it now, CB is the BC that we want to determine. So it has chosen for us about which triangle are we going to use for BC. Because we will say now, I think now we are allowed to just say BC, which is CB in other terms, which is CB or BC divided by CD. Because those two sides are corresponding. And then after we said CB divided by CD, we have to look for another side from this triangle that is going to be the numerator on the right-hand side, and another side on this triangle that is going to be the denominator on the right-hand side. The information that we have is going to decide for us about which side do we choose, because there we have side CE that we can choose. We also have side BE that we can choose. So the given information will decide for us. Let us observe on that sketch over there, on that diagram. Between angle CE and angle BE, which one do we have? Between side CE and side BE, which one do we know?
CE.
CE.
Yep, we know that side CE is equal to 8. So that chooses for us that, okay, between CE and BE, the side that we have to pick is the one that we know. Because BE, if you look at BE, we are not given the units of BE. So we are going to say CE divided by, once we choose CE, by default, we already know which side we are going to choose on the left, because it has to be the side that corresponds to CE. And that side is CB, which is BC basically. BC. And this has to have a reason for, you have to, it's a claim. So any claim that you make in mathematics, it has to be accompanied by a reason. And that reason can be similar triangles. That is an acceptable reason, I think. If there are examiners in this Zoom or on Facebook, please forgive me if this is not acceptable, but I think it is. This reason says similar triangles because that is what we have just used, similar triangles. So when this basically says when triangles are similar to each other, their corresponding sides are in proportion. That is what this means. When two triangles are similar to each other, then their corresponding sides are in proportion. So let us substitute. BC is the one that we want, divided by CD. We are told CD is equal to 2, CE is equal to 8, BC is the one that we want. So we cross multiply, we get BC squared, we get 2 times 8, I think that is 16. If my brain is working well this morning, it has to be 2 times 8, which is 16. And then we take the square root of that BC squared. I think we will get, okay, my pen is not working. And the square root of 16, I think that has to be equal to 4. So BC is equal to 4 units. Are there any questions so far with regards to what we have done with BC? Like, so far so good, né? We are doing the last question now, which has 4 marks. So if you have been understanding the previous question, the previous questions that we answered, if you have been understanding and if you have been comfortable, that means out of 17 marks, you would have received 13 marks. And that's a wow. So that means when you go into that exam tomorrow, or not tomorrow, on Monday, please don't forget what we have discussed here, because it will come handy. It will be important for you on a Monday. So let us deal with DP. Let me give you an opportunity to think as well. What do you think? How do you think we should calculate DP? What's your idea? Any idea? We want DB. Remember, DB is still part of what we have proven in those similar triangles. That might be a hint, I'm not so sure. Any ideas?
We could get the BE first and then use Pythagoras.
We want DB, which is that side. We can get BE first and use Pythagoras. Okay, so how do we get to BE? How do we get to BE? I understand your suggestion, because DB is on the other side and BE is on the other side, and we know what is DE. We have just proven that BC is 4 units. I think that is the information that we should not leave behind. BC is 4 units. Any ideas?
We say
Nothing.
BC over DB equal to CE over BE.
Okay, let me write that down. You say DB?
No, BC
BC
over DB
over DB
equal to CE
CE
over BE.
over BE.
Yes.
You say, what is the reason for that?
Means similar triangles.
Yeah,
In size and
similar.
proportion.
Sorry?
In the size and proportion. I don't know.
You can say sides are in proportion. You can say similar triangles. In my view, I think that sums up into one conclusion or into one claim. So you said BC divided by, so you said BC divided by, okay, I'm trying to track what you did. Which BC did you use? The one on the left or the one on the right?
Which what?
Which BC did you take? The one on the left or the
one on the left?
Oh, okay. So you said BC divided by,
But
I think BC though is supposed to be divided by CE.
Yeah, you're right.
Yeah, because CB corresponds to CE. If you took the BC on the left, then on the right you should take CE. I think that is what we have taken though on this side on the right, which is you said CE divided by no. I don't think this combination is correct.
It's not a correct combination.
Yeah, it's not the correct combination. It's like you did it with using the proportionality theorem. I think, yeah. I think at the back of your mind you had a proportionality theorem.
Sir.
Okay.
What are we looking for now?
We are looking for DB.
Okay.
We are looking for. Hello?
Aren't we looking for BE?
No, at 10.2, at 10.2.2, it's DB.
Okay.
You wanted to come up with a suggestion? how about we use this method? We say BC divided by, which is that BC. We say that BC divided by CE, which is that CE on the other side. And then we say DB divided by BE. DB divided by BE. Do we think that is the correct combination?
Yes.
Okay. Remember what you said earlier on, that we have to sort of find BE first and then use Pythagoras on that right-angled triangle. You were absolutely on a right track, but I wanted you to take me there. So what we are going to do is exactly that. We will sort of find BE, or we will sort of express BE in terms of that DB. So we already know what is BC, right? BC is equal to 4, and we already know what is CE. What is CE?
8.
CE is equal to 8, and this sums up to 1/2, right?
Yes.
Let me write it in this way. So we substituted on the left-hand side with BC with 4, and there is BC with 4. CE, we know that CE is equal to 8, so we substituted the denominator by 8. Then we say DB is over BE. Remember, DB is the one that is in question, the one that we want to determine. Also, BE is the one that we say it is on this right-angle triangle. So it will be a good thing for us to express that BE in terms of that DB. That is what we are going to do. We're going to express that BE in terms of that DB. Then we use Pythagoras. So this will be 1/2 equal to DB over BE, and then we cross multiply. So when we cross multiply, we will get a BE equal to 2 times DB. Can you see that this is the expression of BE in terms of DB? So on that side now of BE, that long side, we can say that side is equal to 2 dB, that side. And then when we use Pythagoras, we're not necessarily going to use BE, but we're going to use the 2 dB, because that is what we want to solve for. That is what we want to solve for. So what comes next now is the Pythagorean theorem. We will say, what is the hypotenuse in that triangle? Triangle DBE.
DE.
DE, yes, is the hypotenuse. DE squared, the one that we want. We do have DE, is equal to DB squared plus BE squared. What is the value for DE? I think we were given DE.
6.
which is equal to 6. And then what is the value for dB? dB is the one that we are calculating for, right? And then in the place of dB, what do you think we should put there as a substitution?
2 dB.
2 dB. So now that equation is in terms of dB. So basically we can solve for dB in this case. So you see the idea that you had earlier on that we should determine that side BE first and then use Pythagoras. That was an absolutely good idea, but I had to give you time so that you take me there. So this is how we get there. The left hand side will be 36, and then dB squared plus 4 dB squared, and then that will give us a 36 of 5 dB squared, and then you divide by that 5. When you divide a 36 by 5, you will still get a 36 by 5, I think. And then that will be equal to a dB squared. And then you take the square root on both sides, take the square root on both sides. And then that should give you an answer of dB equal to 6 over root 5. So that is where we started. We started by saying BC. We started by using the similarity theorem. BC over CE is equal to dB over BE. And then we substitute the values that we have, 4 over 6, and then we simplify that and express BE in terms of dB. And then we transition to use that now in that triangle with Pythagoras, using Pythagoras. This one was a little bit exciting. It was quite tricky. In fact, this was the last question. I think this is from 2020. This is the exam that was written in 2020 last year. So this was the last question out of everything that was there. So it had indeed to be a little bit hectic than other questions. Are there any questions before we move to the last question of Euclidean geometry? Any questions? Okay, I think we, sure.
Do I have to leave my answer in third, or can I just put it in decimals?
Well, the memo always has, well, not always, but on some cases, the memo has both the set form and the decimal. So okay. I think you are covered if you write it as a decimal or you write it as a set form.
Okay.
Another thing, you must be careful with the question. The question will say, what is the ratio? And then a ratio has to be something over something. So preferable when they say what is a ratio, you must leave it in a sort of a fraction format. Numerator and the denominator when they say what is a ratio. But when they say like calculate a value, I think it can be in any format.
Whenever someone
I think let us move to the next question.
Like this lesson, I feel really good.
Hello, you are still unmute.
Right, you need to mute.
Thank you. This is question 9.2. 9.1 was about a proof of a theorem, the theorems that you did in grade 11. So I did not want us to stress more about the proofs in this session, so that we can save this session for applications. So I did cut out that 9.1. So it forms part of this 9.2, that 15 marks. So basically that proof was 5 marks. This question is 10 marks. So let us dive into this question. Also, well, again, what we are going to do is the proper analysis of the given information. Chord UN, there is chord UN. We are told that it bisects angle MNP and intersects chord MP at S, intersects chord MP at S. QN, there is QN, bisects angle MNP and intersects chord MP at S. So that is the first set of information that we receive. So the first thing is very important, the first one. They say that QN bisects angle MNP. That is very important. When they say angle MNP is being bisected, what do you think that means?
The angles are divided.
Sorry?
Angles are divided equally.
Yep. MNP is divided into 2 equal angles. That means angle N1 and angle N2 are actually equal. The reason for that is because we are told that QN is the bisector of that angle MNP. So that's something might come up handy as time goes by. So let us proceed with the statement. We are told that the tangent at P, once you see the word tangent, you know what should come at the back of your mind. Once you see the word tangent. So they said the tangent at P meets MN produced at R, tangent P. The tangent at P meets MN produced at R. There is MN produced, and then MN meets that tangent at R, such that QN is parallel to PR, such that QN is parallel to PR. So there are a lot of information that is given there. Let us unpack it. The first, the second one, we are told that there is a tangent there, which is PR. And what do we know about tangent? Who wants to take a guess? What can we conclude about this tangent and this chord NP? What can we conclude about that tangent PR and about that chord NP? Hello?
P1, the angle of P1 will be equal to M2.
The angle P1 will be equal to?
M2.
M2. So that is the angle between the tangent. Thank you very much for that. The angle between the tangent and the chord is equal to the angle subtended by that chord in the alternate segment. And we have said that that alternate segment in this case is M2. So we are saying that P1 is actually equal to M2. The reason for that, we are saying it is tan chord, meaning that M2 is one of the angles that are equal to X. because P1 is X. Is there any other angle that is also subtended by that NP, that chord NP?
Yes. Q2.
Which angle is that? Q2, right? If you look at NP, NP subtends M2, it also subtends Q2. So also P1, which is the angle between the tangent and the chord, that P1 there is equal to the angle subtended by that chord in the alternate segment. And that second angle is Q2. So we can be confident and say that Q2 is also equal to P1 for the same reason, tan chord theorem. That means Q2 is equal to X as well. So let us proceed and analyze the last set of information that is given. We are told that Qn, where is Qn? Let us look for Qn. There is Qn. We are told that line is parallel to that PR. So when they tell you about parallel, everything that revolves around parallel should be active at the back of your mind. There are a lot of things. There can be alternate angles. There can be corresponding angles. There can be, what do you call it? Co-interior angles. Corresponding angles, co-interior angles, and alternate angles, what you call fun, or what you used to call fun. So there are a lot of things that should pop up at the back of your mind when you see the word when you see the word parallel lines. So there is Qn, there is PR. What do you see? Are there any alternate angles? Are there any corresponding angles before we get into the questions?
Yes, is alternate angles.
Which one do you see?
P1, which is X, equal to N2.
Yep, that is absolutely correct. If you look at it, there is the parallel line, there is the parallel line, more like there in that Z that you have. The parallel line is on the left, the parallel line is on the right. The parallel line is on the left, the parallel line is on the right. And then these two parallel lines are joined by some straight line, and then they form as sort of a Z shape over there. And then once you see that Z shape, you must be reminded of alternate angles. That is P1 is equal to N2. The reason for that, it's because these two angles are alternating. These two angles are alternating. That means N2 is equal to the black line as well. And remember we said, so P1 is X, that means N2 is X as well. But remember we said N1 and N2 are equal. Those two angles are equal because that MNP, that angle MNP is bisected. So if N2 is X, that means N1 is X as well. Do you understand that part? Or should I explain it again? Do you understand why N1 is X?
Yes.
Yes.
Okay, no, that's good. Well, I think we are done with the analysis of the given information. let us get into the questions and see if are there any questions that we have answered before they were even asked. Let's dive into, okay, my pen is giving me a hectic time. 9.2.1 A. They say that determine the following angles in terms of X, give reasons. I think I will take a back seat here and let you write. Who wants to go first? How can you express N2 in terms of X?
N2 is X.
Sorry?
N2 equals X.
N2 is equal to?
X.
Yeah, well, the first thing that you have to say is, okay, this pen. The first thing that you have to say is N2 is equal to P1. And then you write the reason. What is the reason?
Alternative angles.
Alternate angles. Yep.
Angles.
And then you say, therefore, N2 is equal to X. So let us move to number B. Thank you very much for that answer. Who wants to take another guess? Well, a little bit informed guess in this case, I must say. What is Q2 in terms of X? Preferable a different person from the previous one.
Q2 is equals to P1. 10
Yep.
theorem. Q2 is equals to P1.
Is equal to P1. You say the reason is tan
chord theorem.
Chord theorem. You will write theorem. And then you say, therefore, Q2 is equal to X. This is something that we have discovered when we were analyzing that given information. I think we can all agree. So that is where the power of proper analysis of a given information lies. You end up answering questions before they are even asked. So I would recommend that you do that analysis. I would really, really recommend that you do before you even rush into the questions. So now let us get into 9.2, of which I find it interesting. 6 marks there. 9.2.2. Look at that. Look at that diagram. 9.2.2. We want to prove that Mn is equal to Nr, which is equal to Ms over Sq. Most of the time, the thing that you want to prove, it's also a hint to you. You have to use this, you have to use that, you have to leave this, you have to not use that. So the given information, the information that you have in the information that they say prove is basically a hint. There's some insight that you can collect from that information. So let us look at what we want to prove and look at it carefully. Look at what we are required to prove and look at it carefully. We want to form that ratio. Also, look at that diagram. In mathematics, especially in grade 12, there are two theorems, I think, that will allow you to sort of have ratios. The first theorem is the similarity theorem. When there are triangles that are similar, then you can obtain ratios there. Another theorem that will allow you to have ratios is the proportionality theorem, which is the theorem that is applicable when there are parallel lines in a triangle. So the first one is about similar triangles. The second one is about parallel lines that exist in a triangle. So look at what we want to prove, look at the diagram that we are given and reason through. Which theorem are you going to use and which sides are you going to consider? So when you observe the diagram, you see that, oh, there are actually parallel lines there. So the presence of parallel lines suggests the use of which theorem between the similarity theorem and the proportionality theorem. If there are parallel lines, which theorem do you think we should use?
Proportionality.
We should use a proportionality theorem. That is absolutely correct. Thank you very much. So we see that there is PR, which is parallel to QN. And that is, sorry?
Just a quick question. I know you said you took 9.1 out. So since 9.2 is basically about, well, proportionality now, was the 9.1 proof the proportionality theorem? I mean, the proportionality proof?
I think so. I think so.
Okay.
I can't recall with certainty.
Okay.
But yeah, I think so. It was around, yeah, I think so. Yeah, because normally they ask you a proof or they ask you to complete a statement of a certain theorem, and then they ask you to use that theorem below that, that proof or that statement that you've completed. So yeah, I think it's likely that they asked the proof of proportionality theorem above, but I'm not so sure with certainty. Okay, we have established that there are parallel lines, and then that suggests that we might use the proportionality theorem. So now let us analyze the thing that we want to prove and see which sides are we going to use. Let me clean up my table, my diagram. Let us analyze that that thing, that expression. There is Mn, there is Mn, which looks good. So if we use Mn, we might use Ms as well, because the thing about proportionality is like similarity, is like similarity theorem. If you see that you will use Mn, and this is a parallel line, that is a parallel line. If you use Mn, that might suggest that you will use Ms on that triangle. Triangle M, P, R, M, P, R. That triangle. So if you use Mn, that might suggest that if you use that Mn, that might suggest that you will use that Ms. So let us look at what we want to prove. There is MN, okay. There is MS. Oh, that's nice. There is NR. There is NR there, okay. NR over there. And now if we use NR, which theorem is being such? Which side do you think should go along with NR? Any guess? SP. That's absolutely correct. That is SP. And even though in that expression SP is not there, we have SQ. But we are happy because MN is there, MS is there, NR is there. The only side that is not there is SP. So I don't think we should be shaken by that. We might be required to find some way that we can conclude that, okay, SP is indeed equal to SQ. We might want to get there at some point. But for now, let us just create the expression, the ratio. MN over, we're going to divide MN by what? According to the diagram.
NR.
MN divided by NR, that's absolutely correct, is equal to what?
MS over SR.
MS over SP, absolutely correct. SP. What do you think is the reason for this conclusion?
Proportionality theorem.
Proportionality theorem, you can write there, proportionality theorem, blah, blah, blah. You will write it in full. So now we see that, okay, we are happy with the numerator, we are happy with the denominator, we are happy with MS. The only thing that we are not happy with is SP. So we might somehow try to find or establish that SP is equal to SQ so that we can substitute in the place of SP by SQ. Maybe that is what we have to do next. So how can we get there? Let us observe that diagram. I think it's beneficial that I clear it up now and then bring back the angles that we had. So we said Q2, we said Q2 is X, we said M2 is X, we said N2 is X, we said N1 is X as well. Also, we said P1 is X. So how can we conclude that, how can we actually prove that SP, which is that side, is equal to SQ? How can we prove that? I think we have to get there. That is the only way. We have to go through that route. I want you to take a guess. Hello, can you unmute yourself? Thank you. I think the route that we have to take is to show that this SP, which is that line SP, is equal to that SQ, which is that line SQ. So that we can, in the place of SP, substitute by SQ. But we can't just substitute without knowing that they are actually equal. How can we establish that SQ and SP are indeed equal? SP, SQ. Should I give you a yellow? Okay, you were saying something.
Is it congruency?
Is it congruency?
Not.
Hello?
Of a triangle.
You are saying that we should take the root of congruency.
Yeah, is that gonna work?
I'm not so sure. I'm not so sure. I think my thinking process is more fixated on the short method that I have seen. I think there's a better or a little bit of a shorter way. Let me give you a hint. There is SP and there is SQ. Well, there is SP, I mean, and then there is SQ. So if those two lines are equal, what would happen to angle Q2 and angle P3?
They'll be equal also.
They would be equal. So if SQ is equal to SP, if they are equal, then Q2 and P3 would be equal. We would see by Q2 being equal to P3 if SQ and SP are equal. So let us now check if these two angles are not equal or not. What is Q2? Remember, Q2 we said is X, right?
Yes.
Can we determine P3 in terms of X? Maybe that P3 is X as well.
Sir, would I be able to say that P3 is equal to X? Well, P3 is equal to N1 because of angles in the same segment.
Correct. Absolutely correct. That is exactly the right answer that I've been looking for. So what we are going to say, thank you very much for that. It's absolutely correct. And sorry for cutting you short. I got carried away by the excitement. So what we are going to do is that we are going to show that Q2 and P3 are equal. And once we establish that Q2 and P3 are equal, then we can conclude that SQ and SP are equal. This will be an isosceles triangle. It will be an isosceles triangle. So let us say Q2 is equal to X. This is something that we have proven before. Nothing new. And then P3 is equal to N1, which is equal to X. The reason, you said what is the reason for that?
Angles in the same segment.
Sorry, angles on the same segment. Yeah, that works as well.
Yes, sir.
Or angles subtended by the same arc or same chord. That works as well. So let me write your reason. Angles on the same segment. You will write segment properly. I don't have space. I'm trying to accommodate for that. Then we say, therefore, hello?
Would we have to start the question with like when we're answering, do we have to start with angle Q2 is equal to X?
I think so.
Okay.
I think so, because when you show that two things are equal, it's important that you determine one angle alone, determine another angle alone, and then compare if they are equal or not. Then say therefore Q2 is equal to P3, which is, well, you don't have to write the reason. If you want to, you can say which is both equal to X. Can you please unmute? Thank you. And then when these two angles are equal, that means that means SP is equal to SQ. Therefore, we can substitute the N over N R is equal to MS, and then in the place of SP, we substitute SQ. And this is exactly what we wanted to prove over there. That's 6 marks. Nice. So are there any questions with regards to this one? This is the last question that we did for Euclidean geometry. I think we will jump very quick into trigonometry, because I don't want to keep you long at the same time. And at the same time, I don't want to rush the process, because you will end up sitting in a 2-hour lesson and learn nothing, because I'm trying to rush through the material by all means, and that is not what I want. Are there any questions so far with what we have done? Remember, we are concluding. This is the last exercise that we will do in Euclidean geometry. So you can ask any question on Euclidean geometry, whether based on the things that we have done or based on the things that we did not do. Just anything that you would like to ask about Euclidean geometry before we go to trigonometry. No questions. I love questions. So you're hungering me now when you don't ask questions. You're making me hungry. The more we engage, I think the more we learn. The more we engage, the better.
Sir, did we only do two questions?
Sorry?
Did we only do question 9 and question 10?
Yeah, we did 2 questions. I don't know whether it was question 10, the other one. Yeah, it was 10.
Yeah. Okay.
Yeah.
I'm just making sure. Okay.
Yeah, but I think these are a little bit, covering a lot of familiar questions when it comes to the standard of the exams. Because you can expect in an exam to be asked about ratios. You can expect in an exam to be asked about similar triangles, proving a cyclic quadrilateral and expressing certain angles in terms of x and stuff like that. So I think this covers more like a lot of things that you would expect in Euclidean geometry. So let's go to trigonometry then. I picked this one as well because it has more like a lot of what you can expect in trigonometry.
Sir,
okay.
Just a quick question. What about when we have 2 circles?
When we have 2 circles in Euclidean geometry?
Yeah.
Okay.
Would we still use it the same way?
Yeah, you will use it. You will use the knowledge that you have learned here the same way that we did here. You will apply it there.
Okay.
The key that I think is one of the most important in Euclidean geometry is the proper analysis of the given information. If as much as there are 2 circles, or there's 1 circle, or there are 3 circles, I think all of them revolve around the same thing: circle, quadrilateral, diameter, tangent, chord, angle at center, ratios, and stuff like that. So if you understand your foundation, and then you are able to use it when you analyze that given statement, then everything is likely to go smooth. Is likely to go smooth.
Thank you, sir.
Should we get into trigonometry?
Yes, please.
Are we alone? Are still people around?
Yes, so here.
Yes.
Oh, okay. That's nice. The thing is, I can't see. I only see what you see there, the whiteboard. I can't see anything at the back, whether people are still around or there are questions or hands raised. So let us dive deep into what we call trigonometry, which also is one of the chapters that have a lot of marks in paper 2. So if we look at that question 5.1, if you look at that question is something that is so familiar. You might expect to have such a question on a Monday. If the question is not in that format, the one that is on 5.1, then it is likely that it will occupy the format on that question, which is 5.4. Or if it is not the format that is on 5.4, then you might be given a question whereby, let's say, a sketch has been drawn already for you, and then you have to analyze the sketch. Let's say maybe they say that is point P, and then they say X is 4, or something like that, or whatever coordinates, X, let's say M, stuff like that, and then they tell you other details. And then from that sketch, you answer questions that follow. So these questions, the very first question in trigonometry is normally, one of these 3 formats. The first one, whereby they say sine 16 degrees is equal to P, and then you answer questions, you express them in terms of P. The second format is whereby you have to draw a sketch on a Cartesian plane. Well, you still draw a sketch even on the first format, but not necessarily on the Cartesian plane. But on a question like that, you are required to draw it on a Cartesian plane, because you have to pick quadrants and stuff like that. And then if it is not one of these 2 formats, you will be given this format whereby there is a graph already drawn for you, and then you analyze it and answer the questions. So this question paper has these 2 formats. That's why I liked it. So let us move forward and dive deep into 5.1. When it comes to 5.1, you are given that sine 16 degrees is equal to P. It's important that you remember that P over there has a denominator of 1. Keep that in mind. And now, when it comes to the definition of the sine, we see that P is going to be the opposite side to that angle 16 degrees. That P over there is going to be the opposite side to that angle 16 degrees. And that one is going to be a hypotenuse. So we will draw a sketch. We don't necessarily have to draw this one on a Cartesian plane because we are given the angle, which is 16, which tells us exactly that, okay, the sketch has to be in the first quadrant because this is an acute angle, 16. And then there is our sketch. And then the angle at that corner, the base there is 16 degrees. 16 degrees. And then remember we said that the opposite side to that angle, 16 degrees, has to be P. And then the hypotenuse of that triangle has to be 1. And then we are done filling in the given information. Now, there are a few things that we have to calculate though. What do you think we have to calculate? The first thing that we have to calculate, who wants to take a guess, and how can we calculate it?
Are we not calculating the, what's this thing? The other side that we don't have, so it's what opposite?
Yes,
It
is
adjacent,
adjacent side. Yep.
Yeah, and then we're going to use Pythagoras for that.
Excellent. We will say r squared is equal to x squared plus y squared. R is 1. What is x? What is x?
P?
No, x is the one that we are looking for.
Oh, okay.
R squared r squared is equal to x squared plus y squared. R is 1. X is the one that we are looking for. Y is P, which becomes P squared. And then it becomes 1 minus P squared equal to x squared. So now we take the square root because we do not want x squared, we want x. So we take the square root. Remember, when we take the square root, we include the entire expression on the left. Don't take the square root of 1 and then you say minus square root of P squared. It does not work like square root of 1 minus square root of P squared. It does not work like that. It has to be the square root of the entire thing on the left. Then we know that x is equal to the square root of 1 minus P squared. So in our diagram, we have the horizontal side, which is x, as the square root of 1 minus P squared. What do you think is still missing there in that triangle, and how can we calculate it?
Are we going to look for the other angles though?
Yep, we're going to look for the other angle.
So you're going to say 180 minus 90 minus 16.
Yes, 180.
And why are we looking for it?
Yellow?
Why are we looking for the other angle?
It might come handy when we are answering those questions.
Oh, okay.
We don't know yet. So it will be 180 degrees minus 90 minus 16. What are you getting?
74.
No, where are the learners? I don't want a quiet class. Where are the learners? Okay, well, let's move. We have 5 point, well, we are done with the diagram now because it is complete. So let us go to 5.1.1, which is we determine in terms of P sine of 196 degrees. How do you think we should tackle that one?
(180 minus 16).
Is it minus?
180 plus 16.
Yep, it's 180 plus 16.
Yes.
How did you get to 180 plus 16? I want your thinking process. How did you get to 180 plus 16?
180 plus 16 is equal to 196.
Okay. You see, if you that's a good answer. If you look at that angle, 196 degrees, it is on which quadrant? If we have a quadrant there, 0 degrees, 90 degrees, 180 degrees, 270 degrees, and 360 degrees.
The third one.
100. Sorry?
On the third quadrant.
On the third quadrant, what is the reduction formula at the third quadrant?
(180 plus).
The reduction formula at the third quadrant is 180 degrees plus x. That is absolutely correct. That is why we use 180 degrees plus 16. That x over there is one of these two acute angles in that sketch. You ask yourself, where is 196 degrees in a Cartesian plane? You move from 0 to 90 to 180, and then you approach 270, and then which means you are around there in the third quadrant. And then you ask yourself, which reduction formula is in the third quadrant? That is 180 degrees plus x. That x is one of the, might be one of those angles that are in that diagram. And in this case, we were lucky to find out that it's actually 16. So that means we can replace 196. We can replace 196 with 180 degrees. With 180 degrees plus 16 degrees. And then we reduce that angle using that reduction formula. What is the sign of sine in third quadrant? Is it positive or negative?
Negative.
That is negative. And then it will become a sine of 16 degrees. And then now we can go and read sine 16 degrees from that sketch very easily. Or you can even take the one that you were given, because sine 16 is given as P. Then sine, then this turns out to be a negative P. So that is how we got there. I think 5.1.2 is very easy. What is cos of 16 degrees?
It's the square root of 1 minus p squared over 1.
Yep. Cos 16 degrees is quite simple because it is the adjacent side of that angle 16 degrees. And the adjacent side is 1 is square root of 1 minus p squared all over 1. That is the answer for 5.1.2. Yep, let us then move to 5.2. Are there any questions on this one? Any questions?
I have a question.
That's good. I enjoy questions.
So for 5.1.2, is the final answer square root 1 minus p over 1? We don't have like a minus 16.
No,
because
we don't.
Why not?
We used to go the sketch.
We used the sketch.
Okay.
Okay. Tell us your view. Where do you get the minus? What do you think we will take the minus?
No, because for sine 196, right? 6 p is negative in there, right? Because sine is in 180 plus, not 180 minus, not 180 plus. And then in the cos quadrant, it's 360 minus. So then
the thing is, we are dealing with angle 16 degrees there.
Okay.
We are not dealing with angle 196 degrees.
Okay.
So there is a difference there.
Okay.
If you look at that 16, which is an acute angle, that angle 16 is in the first quadrant, and cosine is positive in the first quadrant. Hence, there is a positive there.
Oh, okay. Okay, I understand.
Yeah.
Got it. Thank you.
Thank you. I think let's move to 5.2. 5.2. Yeah. You can start thinking about it as I am cleaning the slide, this copy of the slide. We will talk about compound angles there at 5.2. It's unfortunate that my board has a limited space. Very unfortunate. But we will do it nonetheless. Are there any ideas as to how we can go about solving that 5.6? It's quite simple though. You are given that cos, you are given that compound angle expression for cosine, and then they ask you to use that compound angle expression for cosine to derive a compound expression for sine. So that is what we are going to do. This will demand a very big space for me. So we are given that cos A minus B is equal to cos A cos B plus sine A sine B. So that is what we are given, I think, yeah. And then we are required to prove that we are required to derive a formula for sine A plus beta plus B, I mean. So I think the first thing that you notice there is that the expression that we are given is that of a cosine, not a sine. So our duty then is to first change this sign that we have, or this sign that we are asking, and express it in terms of cosine. And we can do so using 90 degrees minus. So if we change this angle A plus B to angle if we change it to angle, oh, my pen. If we change it to angle 90 degrees minus A plus B, if we change that angle, the one that we have, which is A plus B, we change it to a 90 degrees minus A plus B, then that sign has to change to a cosine. I think you can recall this. This is something that can be simply written as cos 90 degrees minus x is equal to, what is the expression of this? How can you change this? How can you change it from cos of 90 degrees minus x? What will be the answer on this side?
Can't you just take the minus out?
It will be?
Like minus cos x minus 90.
It will be? I did not hear you.
Minus cos x minus 90.
No, I don't think it will be like that.
Or when you convert it to sine.
Hello? This is a reduction. It's part of reduction formulas. 90 degrees minus x is part of the reduction formulas. So when you have a 90 degrees minus x, you will have to reduce this 90 degrees minus x to x. But when you do so, this ratio, which is cosine, will have to change to a what?
Sine.
Will have to change to a sine of x. So that is how we got into the expression above. We want to, can you please unmute yourself? Can you please mute yourself? Makazi sicela
No.
Hello? Hello?
They muted, sir.
No, I was just muting the people that were making noise at the background.
I don't think she had her phone with her.
I've just muted them. Can you still hear me on the other side?
Yes, sir.
Yeah.
Oh, very well. So what we want to do here eventually is to reduce that sign to a cosine, is to change it, is to change that cosine to a sine. So if we have a sine, then we have to change that sign to a cosine using this expression. So this is what we did there basically. In the place of a plus b, that a plus b, you can assume that it is x. And then what we are going to do now is to expand this thing. We're going to say cos, we take 90 degrees minus b. Well, we multiply out first by that negative. We multiply out by that negative 90 degrees minus a minus b. And then we say cos. We factor out that 90 degrees minus a. We put it aside as a separate angle or as a united angle. And then 90 degrees minus a minus b. And then now we can use the thing that is given, because the thing that is given is in terms of cos. Now we have cos, and our a, and the expression that was given is in terms of a, and our a in this case is 90 degrees minus a. And the b is still b even in our case. So the only difference in this expression is that a, in our case, we have 90 degrees minus a. In their case, they have a. They have cos, we have cos. They have a, we have 90 degrees minus a. They have b, we have b. So that is what we are going to use to expand this expression. So the way they expanded it is that they said cos, then it becomes cos there, which is cos. Cos of which angle? Who wants to take a guess? For us, it will be cos of which angle? For them, it is cos of a. They used that a. So for us, it will be cos of which angle?
90 minus a.
90 degrees minus a. That is absolutely correct. It will be followed by a cos of what?
B.
Yep, it will be followed by a cos of b. And then the negative here, they also have a negative, we also have a negative. So they changed that negative to a positive. That means we have to change it to a positive as well. And then what is following? What do you think comes next? They have a sine a. What should come for us? They have a sine a, and there is their a. What do you think will come after our plus?
Sine 90 minus a.
Yep, it will be sine 90 degrees minus a, and then multiplied by a sine of b.
Yes.
And then we reduce this thing, this expression. Remember, we said cos 90 degrees minus x is equal to what? A sine x, right? So a cos of 90 degrees minus a will be reduced to a sine of a. That cos has to change to a sine because we are dealing with a 90. Followed by a cos of b plus, we are dealing now with a sine and a 90 degrees. That means that sine has to change to what?
To a cos.
To a cos of a. Multiplied by a sine of b. So that is what we wanted to prove, that sine a plus b is indeed sine a cos b plus cos A sine B. So this is what we wanted to prove. And we have done just that. And we did it using the given information. The given information. So let us then now move to the simplifying stage. Are there any questions with regards to what we did here?
No.
Okay. I think the time now is 11:30. I think, how about we close at 12? I don't want to keep you here. I don't want to keep you here the entire day.
Yes, sir, it's fine.
Yeah, no, let's work towards 12. We've been here since 9, is 10, 11, 3 hours. Yeah, eh? That's nice. Really nice. So now let us go to the simplification question. Is 5.3. Can you please unmute yourself at the back? Thank you. We have that expression there. Square root of 1 minus cos squared 2a all divided by cos of negative a. This is 5 marks. It's quite simple. It's one of those things that you are like, they're just saying in 3 marks. Mahala. So let us simplify. What do you think we can do to simplify the numerator? What do you think we can change there? Any ideas? Am I still with learners? Are there any learners in the session?
So the cos 90 plus a can be negative sin a.
No, I'm still asking about the numerator. The one at the top. You remember in grade 10, there was something called an identity, which is sine squared x plus cos squared x. That is equal to what? Hello?
Equal to 1.
That is, yes, that is equal to 1. And now when you solve for the sine of x, you should be getting, when you solve for sine squared x, you should be getting what? 1 minus cos squared x, right? What do you think is the difference between the expression that we have on the right-hand side and the expression that we have in the numerator. What do you think is the difference?
The 2a and the cos square x, because now you only have 1x, but on the other side you've got 2.
Absolutely correct. Now the angles have changed. The expression from grade 11 has an x, and the expression from this thing that we want to simplify, the angle there is 2a. But the narrative remains the same, really. Because if we were to accommodate there for that 2, we would just write the 2 next to that x, write the 2, write the 2. Then it is the same. The narrative remains the same. Sine squared x, we would just write the 2 there. So can you see now the expression on the right hand side, which is 1 minus cos 1 minus cos squared 2x. That 1 minus cos squared 2x is equal to sine squared 2x. That 1 minus cos squared 2x is equal to sine squared 2x. So linking that now to what is in the numerator, what do you think is the best substitution for what is under that square root? What do you think is the best substitution?
Sine 2x.
Yep, definitely. Now we're getting it. The best substitution has to be sine squared 2x. No, not 2x. 2a, because the angle that we are using is a. And then now we can go to the denominator. Someone had a suggestion about the denominator. I would love to hear it.
The cos 90 plus a can be written as then a.
I'm losing you because of the network connection on your side, I think. You were saying?
So cos 90 plus a can be written as negative spin a.
Yep, absolutely correct. She's saying that on the denominator there, that 90 degrees plus a is in the second quadrant in the cast diagram. That 90 degrees plus x is in the second quadrant, and cosine there is negative. Hence, there will be a negative there in the denominator, a negative. But now we have a cos and we have a 90. That means something has to change, which means that cos has to change to a sine of a. And then I always advise that you put brackets once you see a negative. Try to put brackets by all means. So we have dealt with the numerator and then the second part in the denominator. What about the first part in the denominator, cos of negative a?
It's cos a, positive cos a.
Yes, it will remain as cos a because negative a is in the fourth quadrant and cosine is positive there in the fourth quadrant. Hence, we will have a cosine of a. Yep. And then we proceed. We take a square root in the numerator, we will be left with sine sine 2a divided by, in the denominator, we have a negative sine a cos a issue. We have that. What do you think we will replace the numerator with? That is sine 2a. What is the best candidate to replace that sine 2a?
Two sin a.
2
and cos
sine
a.
a cos a, because that is a double angle divided by negative sine a cos a. That is a double angle. And then you cancel out, and then you are left with a negative 2. So I think this was quite nice. You just struggled with that part. You got scared because there is a 2a, whereas you are used to just a from grade 11. But other than that, it was quite a nice example. I think let us proceed to 5.4. Let us proceed to 5.4. You can look. Sorry? Were you saying something?
No, sorry, sir.
Okay. Let us go to 5.4. So when we get there, we see that we have a cos 2 beta is equal to a 3/5. And we are told that beta is between 0 and 90 degrees. So which quadrant is 0 and 90 degrees? Which quadrant is that?
The first quadrant.
That is the first quadrant. That means the diagram that we are going to draw for this problem is in the first quadrant. But it will not be a 2 beta that we are going to put there. It will be, we will have to simplify this into a little bit of a better version, whereby it's not 2 times beta, whereby it is not 2 times b. I mean, it is just b. So the way we simplify this, we observe that, okay, 2b is a double angle. So basically we can change that cos 2b, let's say, to 2 cos squared b minus 1 equal to 3/5. And then we try to solve for that cos beta. We try to solve for that cos b and isolate it on the left-hand side of the equation. That means we will take the negative to the right, and then we will divide by 2, and then we take the square root. Because we want the cos b to be on the left. So we will take the negative 1 to the right. That will be 2 cos squared b equal to 3/5 minus 1, which will be equal to, what do we get on a calculator? We also get negative 2/5.
Yes.
And then you divide that by 2. You divide by 2. You divide by 2. You should get cos why is it that it gives me a negative?
Sir?
Hello?
On the second row, right, we said 2 cos B minus 1. And then on the third row, we took the 1 over. However, we left it as a negative. Why did we not change it to a positive? There we go.
Very good, very good, very good. Now, I was just checking if you guys are still awake. Seems like we are following. That's good. So we get 8 over 5, and then we divide right through by 2. We divide right through by 2. And then we get cos B equal to 4 over 5. So what do you think we should do now? Because we want cosine B, not just cos squared B.
Do we put it under a square root?
Yep, we take the square root, and then it becomes cos B 2 over square root of 5. Remember, anything that comes after the square root, right, it has to be plus or minus. But now we were told that the beta that we are working with is between 0 and 90 degrees. That is the first quadrant. And in the first quadrant, what is the sign of cosine?
Positive.
Positive. Hence, we are going to remove the option of a negative here and only be left with the positive. Because cosine in the first quadrant is actually positive.
Sir?
Sure.
I have a question. So like okay. on the cos B equal to 2 over root of 5.
Instead of writing as
2 the square root of 5 over 5.
Oh, you used the calculator. No, I did. I used, I got that answer, that 2 over. When you do not use a calculator, you get a 2 over root 5. When you use a calculator, you get a 2 times root 5 over 5. That is okay, the same.
So am I not supposed to use a calculator for this example?
Well, it did say without using a calculator, but the memos, I think somehow do have even the value that you talked about, which is 2 times 5, root 5 over 5. So I'm not so sure whether they penalize you, even though the answer is in the memo.
Okay.
But I think even if you get 2 times root 5 over 5, I think you have to proceed with the question.
Okay, sir.
So let us proceed with 2 over root 5 for now, because that is, I think that is the safest approach, which is the one where we did not use the calculator. So we are going to make a sketch in the first quadrant. Remember, 2 will be the adjacent side. What will be the denominator? What will be root 5?
The hypotenuse.
The hypotenuse.
Hypotenuse. Yep, that will be the hypotenuse. So now we want to sketch in the first quadrant. Remember, we will sketch in the first quadrant. The information that we are given points us directly to the first quadrant. Oh, my pen. You'll forgive me. Okay. So that angle over there is angle B. And then the opposite, the adjacent side, we said the adjacent side will be equal to what? Well, according to what I'm using here.
2.
2. What about the hypotenuse?
Square root 5.
Square root 5. What about the vertical side? Which theorem do we use to calculate it?
Pythagoras.
We say r squared is equal to x squared plus y squared. What is r? 5, right? What is y?
2.
X is 2. What is y? The y is the one that we are calculating. Are we together?
Yes.
Then to the square root of 5. The right-hand side will be 5 equal to a 4 plus y squared, which will be equal to a 1 y squared. And then a y will be a plus or minus 1. Which one are we going to take, a plus or negative?
Positive.
Plus.
We will take a positive. We will take a positive, y is equal to 1. So we are done with the sketch. Then we can answer those questions just the way we did with the previous question of sketching. I think let me take a back seat and let you do cos B and sin B. And then you can provide answers so that I can stretch myself. What is 5.1, 5.4.1?
Two over root 5.
Cos B is equal to 2 over root 5, which is adjacent of hypotenuse. That is excellent. What is 5.2 sin beta?
1
sin
over
B.
root 5.
Excellent, excellent.
1 over root 5.
Root 5, that is excellent. And then we have that bigger guy there, which is cos B plus 45 degrees. But well, he's not so big. We can bite him piece by piece, which is cos B plus 45 degrees. That is the expression of a compound angle of cosine. How do we expand that expression?
Cos B.
Cos B, excellent.
Cos 45.
Excellent.
Minus sin B. Sin 45.
Yep. So it is not so big after all. So on the first, we will place there the fraction of cos B. I think we determined it previously. It to be 2 over root 5. And then cos 45, I think cos 45 is 1 over root 2, if I'm not mistaken. Your calculator is likely to give you a root 2 over 2. Your calculator is likely to give you a root 2 over 2, but if you do it by head, you are likely, well, you will get a 1 over root 2. Do you see the difference between root 2 over 2 and 1 over root 2? 1 over root 2 is from the head and root 2 over 2 is from the calculator. So we are trying by all means to run away from the use of a calculator. But if you happen to forget 1 over root 2, well, proceed with what you can. The markers will see what to do. Maybe penalize you or be fair at you. It will depend, I don't know. I've never been a marker before. So sign B. Yeah, it's 1 over root 5. And sign 45, same as apply, same as yeah. And then you can add that up together. Well, you can use a calculator in a very stylish way so that they don't catch you that you used a calculator. Maybe you press the denominators together, numerators together. For example, 2 times 1, that is 2. The square root of 5 times the square root of 2, that is the square root of 10, minus 1 times 1, that is a 1. And then that will be the denominator, which is the square root of 10. And that will give you a square root of 10, 2 minus 1, a 1. 1 over square root of 10. It should be that, or it should be square root of 10 over 10. Either one. You can press it there on a calculator. I think it's fine. And then you just jump to that step. And then you exclude those 2 steps. I think it's absolutely fine. Are there any questions with this one? Because this is the last question of this question 5. 21 marks. I think this was a question paper. This is a question paper that was written in 2016. Yes, we did 2020 and we did 2016 November. Nice question. Any questions?
No.
6 minutes left before 12. Now, I don't think we will be able to move to the last question, because this was going to be the last question of trigonometry, which was going to include trigonometric functions and general solution and graphical analysis. But sadly, it's 5 to 12. It's also advisable not to keep you so long in a mathematics lesson, just for the health of your intellectual capacity. I think it's safe if we wrap up. You can come up with the questions that you would like to ask, maybe some clarity here and there, just to wrap up, maybe something that we did not cover, or maybe a comment that you might be having, or anything. The floor is yours, all of you.
Sir?
Anyone?
Since we didn't cover the general solution today, would we be able to do it tomorrow? Because Mr. Sizwe did talk about a Sunday lesson. I'm not sure.
Sorry?
I'm asking, would we be able to do it tomorrow?
Well, I will talk to the team that is organizing these lessons. I will propose a lesson for tomorrow. It will depend if there is a slot or there is not a slot, but then I'll get back to you.
All right, sir.
Any questions? I think I should stop sharing the screen. Close. Stop sharing. And then I can sort of switch on the video just to say goodbye. Any questions? Okay, no. I think we can close then. It was a lovely lesson for me, very interactive one as usual. Let me then say goodbye. Thank you for coming. Thank you for being here up until this time. 3-hour lesson. Yeah, that's a lot.
Yeah, thank you, sir.
See you tomorrow if
Thank you,
it
sir.
happens. We do have a lesson. If we don't, all the best for Monday. Make sure that you read the questions carefully, because everything, well, maybe not everything, but majority of the things that you need lie there in that given statement. So make sure that you make a proper analysis of the given information. Other than that, goodbye.
Thank you, sir.
Afternoon. Sure.